Okay, so hi everyone. Today, this entire week, for week 11, we'll be looking into finite state machines. Okay, oh,
Good morning, ma'am.
yeah, good morning. Okay, so now starting with the finite state machine, okay, the FSM. So till now we have looked into many flip flops, right? D flip flop, JK flip flop, T flip flop, and so on. So first, let's just take an example of D flip flop and try to visualize how we want the finite state machine to be, and I'll explain from there. Okay. So now this is your D flip flop. You have your clock, and now here you have a combinational block. Okay, you have a combinational block, let's say combinational block 1, and this has primary inputs, and then from here the output goes to the D flip flop, D input here, and then from here, right? So this will be your current state. So this output is basically going to this input, and this will be, let's say, this all are n bits, all are n bits. This all are n bits. So what happens is at this point you will have your next state, and at this point this will be your current state. Okay, so again after this is also n bit, and then again I have another combinational block. Let's say this is combinational block 2. This is combinational block 2, and let's say my output is given as k, and this will be my primary output. Okay, so here my another input here, let's say I just want to give the same input, the primary input as another input here. So let me tell this as this m bit, so this will also m bits. Okay, so from here what did you get? N will be the number of flip flops that you're using. Okay, and then you also have m for primary input, and then you use k for primary output. So just remember this visualization. What we'll try to do is we will use examples and try to come to this conclusion, like how we are trying to solve the finite state machines. Now what the finite, now for the timing, and now also remember this timing analysis map. So this is pretty much theoretical, and then we will move on to more practical approach, like using D flip flop and JK flip flop and so on. So now let's say this is my positive edge clock here, and if I am taking this as my primary input, now let's say this is my primary input, and I'm giving this as state 1, then there is a change to state 2. So let's say this is my state 1, this is my state 2, and I have a current state. Current state, okay? So this current state now, it is basically like this. And again here I have my state 1, and then after some time here I have my state 2. And then finally I have my next state. For next state, it is pretty much same like the primary input. So I have my state 1 here, which starts here, and then I have my state 2, which starts from here. Now in this timing analysis, right? So this is clock, and you're having primary inputs, current state and next state. So what happens is basically your clock is the one that drives this current state. Okay, so this current state depends on this clock. When the clock changes, the current state also changes accordingly. And then when the primary input changes, that will drive the next state. Okay. So that's how it works. So you have to remember this also. The clock is the one responsible for current state, and once the primary input changes, the next state also changes. Now we come to the more detailed part, FSM. So in FSM, we have two parts. One is the analysis, and the next one is design. So analysis is pretty much like we have a set of what you tell uh, a state machine given, and we are trying to analyze what are the state transition that happens and what are the outputs that we get according to that state transition. Okay, and design is something like you know what the output should be and you're trying to design a finite state machine. So designing a finite state machine example, like I think we also saw before, like few lectures, the counter, the traffic signal counter. Okay, so this is a finite state machine and that is designing. So we are designing that particular traffic signal counter. So this all comes under design. Analysis is we already have a finite state machine given to us and we try to find out what will be the output and what are the state transition that happens, and when it transitions from one state to another, then what are the inputs and outputs that we have to keep in mind. So moving on to the first example. So first, let's say we are trying to analyze the D flip flop. Okay, for the D flip flop analysis based on D flip flop. So first, this is I have do two D flip flops. This is flip flop one, and I have another flip flop. Okay, so basically this is connected to clock. And then I have a OR gate and the output goes to D, and AND gate, two AND gates here where one is connected to X. This is the primary inputs that we're talking about. One is connected to X and the other is connected to A. Okay, so the other is connected to A, and then we have another output that is A bar, complement of the A. And similarly here also I have B and I also have B bar. So now here, from here I have okay, for this I need two outputs. So I think one input for this will be from B. So this is just an example that we're using to understand the concept. So B, and then we have another input which let's say is going from X. I think okay, X. And then we have for D. Now for this D, I'm using an AND gate. One input is A complement and the other input is X. Okay, now so this 2 is given, right? So all the inputs are given. Okay. And then I have another. So let's say this is combinational block 1. I have another set of combinational block also. That is, I have an AND gate, OR gate, and a NOT. The NOT is from X. And for OR gate, I have A and B. So I'm using where is A. So this is A. Okay. Okay, so I have one A and then B here and B here. Okay. And this final one will result in the output Y. So now here if you see, right, so this entire block here, basically this is combinational block 1. So this will be combinational block 1 if you see from the above one. If we are trying to understand that in this particular perspective, then this will be combinational block 1. And this small one, the second combinational block, will be this part where it will give us to the primary the output that we require. So and this will be combinational block 2. And if you see, the X is a primary input, Y is a primary output. And for D flip flop, we have A bar, B bar is given. Okay. So now in this entire example, if you see, number of flip flops that we have is 2. And then you have number of primary input is 1. Number of primary output is 1. Input and output. Okay. So now what we do is in this entire example, we are not worried exactly about how we are trying to derive this. What we are worried is about all possible state transition that will happen. So if you see there are two flip flops, so the possibility are there are like 0 0 0 1 1 0 1 1. So these are the only four possibilities. But our question is like what are the state transition that when it is 0 0 and when the input is 0, what happens? Similarly, we want the entire state transitions that we want to understand. So now for our next state, right? For our next state, we will define it as it is a function of current state and the input, the primary input. And similarly, the primary output, it is a function of current state and primary input. Okay. So if you see which is the next state will come somewhere over here. Our current state is here. Next state is to this point. Here also this is the next state and this will be the current state. And this is the output. So now what will, okay, now we'll just label this point EF so that it's easier. So now at point E, we want to find what is it at point E. Okay. So now if you see, so at this point for this AND gate, so what is the value here? This here, no, it is A and X. So this will be A. And for this one? BX, right? So the value is from here to here. So it is BX. So this is OR. So what will be E?
AX plus BX.
Correct. So it is AX plus BX. Now, what we know is this E is basically the next state. That is, next state, as in current state. Let's say we're using notation N for the current time. So, AN is at this particular clock cycle, and for the next clock cycle, we will call it as AN plus 1. And the clock cycle after that will become AN plus 2, and so on. So, E will be basically AN plus 1. That will be equal to an, the current state of x, plus bn x. Okay. Similarly, now we'll find for f. Now at point f, if you see, this is an AND gate which has a bar and x. So what is f? F is basically a complement x. And what is f? F is the next state of b. So we have bn plus 1, which is equal to an complement x. And now finally we are trying to find the output y. So if you find output y, so there is a not here, so this is x bar. And then what is this one? There is an or which has this has basically, where is this going? Okay, here. This is b. This is b and this one is a. So this is basically a plus b. So your y will be a plus b to x x bar. Okay, a plus b to x bar. So if you're writing again it in the terms of the clock cycle, so it will be an plus bn x bar. Okay. So now here, this is what we will call it as state equation. So we will call this as state equation. So what are state equations is, the next state is basically denoted in terms of the inputs and the current state. So what all the next states we have? So basically this is one of the next state, a n plus 1, b n plus 1, and finally we have output. So we have a n plus 1, which we found as a n x plus b n x. And then we have bn plus 1, which is equal to a n complement x. And then finally y, which is equal to a n plus bn x complement. Okay. So these are the state equations, and this is how you have to write the state equations. Now there is another concept that we'll be introducing called state table. So for this kind of combinational block with the flip-flops together, which has next state, current state, we cannot write a truth table for that. So we will introduce something called state table. So what state table has is, it will have a present state, it will have inputs that we are giving, then it will have next state, finally it will have the outputs that we are getting. So here in this example, our present states are an, bn, and my input is x, and my next state will be an plus 1, bn plus 1, and my output is y. So it's the same for present state inputs. We will write 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and so on. So we will write the entire table for the present state and the input. Oh, wait. 101, 110, 111. So now for this table, right, where we will get it from here. What is our an plus 1? It is anx plus bnx. So we have our an and we have x, and we have a bn. So now, can you tell me what is an plus 1? It is anx plus bnx.
0,
Yes, and the next one?
0,
Okay, and
0,
yes, and
1,
okay,
then again 0,
0, then 1 0 0
0,
0. Okay, is it 0 or 1? It is ax plus bx. So ax 1, 1 plus 0 1 1. This is 0 and 0 0, and this is 1 1 1. Okay. So now similarly, what about bn? Bn plus 1, what is bn plus 1? It is an bar x. So basically it is an bar and x. So if it is an bar, basically this all the 4 will be 0. 0 0 0 0 0. And whenever x is 0 also, it will be 0, right? So this is also 0 and this is also 0. And this is an bar is 1, 1 into 1, 1. Is there something wrong? This one, no? So this is an bar 1 and 1 will be 1. Okay. So we got our an plus 1, bn plus 1 by solving this equation, and we used an, bn, x. Now similarly for y you have an plus bn and x bar. We have an, bn and x bar. Okay. So now what is our an plus bn? This will be 0 0 0. It is 0. This is 0 1 0. This is 1 and 0 0. 1 and 1 1. X bar, right? So 0 plus 1, this is 1, right? X bar. Y is equal to an plus bn x bar. Then this will be 0. And 1 and 0, 1, and x bar 1. 1 and 0, 1, x bar 0. 1 and 1 is 1, x bar 1, and final this will be 0. Okay? I hope it is correct. So if you see, this is an entire state table. We call this state table just because we cannot have truth tables which has only the input and output. The state table is used where we have present state, input, next state, and outputs. And this entire table, basically this is pretty much enough compared to the state equation. So you have a whole view of what transitions you're getting, right? So that is when from this table we can get into something called state diagram. Okay, now how we are going to get state diagram is from that table here above. Okay, so this present state, this will basically give us our state. So our state is basically so basically here what is A and B and this is basically the outputs of the flip flop, right? This is output of one flip flop, output of second flip flop. So what happens? You have two flip flop, you have two flip flops, right? So how many states will you have? You will have 2 power 2, 4 states. Okay, you will have 2 power the number of flip flop, the number of flip flop. That will basically be your number of states. So now here if you see in this example we're having two flip flops, so the states will be 0 0, then you have 0 1, then you have 1 0, and 1 1. So now for this one, if you see for 0 0, if you see here 0 0 0 0, the input is 0, it will transition to 0 and 0 again, and the output is 0. So 0 0 will transition to itself, and how we will denote it as is, now say, let's say you're writing a state diagram like this. You will have your input slash output. That is how you will write. Okay, so now let's say I'm writing my output in green color and input in red. Okay, so now 0 0, it will transition to 0 0, and my input is 0, and the output will be, output here is 0. Okay, now similarly, if you say now 0 0, it will transition to 0 1. 0 0 will transition to 0 1. Our input is 1, our output is 0. So input is 1 and the output is 0. Okay, so like this way we'll fill the entire diagram. So can you tell me now 0 1 is transitioning to 0 and 0. So 0 1 transitioning to 0 and 0. Input 0, output 1. How do we write it as?
0/1.
Correct. Now next is 0 1. The input is 1. It goes to 1 and 1. Input is 1 and what are we getting? Output 0. Okay, now next one, 1 0. So 1 0 moves to 0 and 0. 1 0 moves to 0 and 0. And here the input is 0, output is 1. Input is 0, output is 1. And then, okay, let's just not cross for now. Instead of crossing, I'll just, input is 0 and output is 1. And now 1 0, it moves on to the same state, 1 0 1 and 0. So moves on to the same state and it is 1 and 0. And then 1 1 moves to 0 0 to 0 0 with 0 and 1. And finally 1 1 moves to 1 0 with 1 and 0. 1 and 0. Okay. So this is our entire state diagram for this particular example. So if you see, we have introduced many terms here. Like first, so what did we do? We had this example. From this example, we found how many flip-flops we have used and our primary input and primary outputs. And after that, we found out that this small one here is a combinational block 1, and the output, the combinational block 2 is giving a output. And then before we get into this input here, that will be our next state, and the output here will be a current state. After that, we found out state equations. So state equations we found for the next state based on the current state and the inputs. And we also found the output. Output is also based on the current state and the inputs. Okay, so that's what we wrote. Next state is a function of current state and inputs. Our output is also a function of current state and inputs. Okay, so we found the state equation, and from this state equation we derived the state table. So we have a present state, input, next state, and output. And once we found the state table, from the state table we came and derived the state diagram. And for the state diagram, the number of states depend on the flip-flops. 2 power the number of flip-flop will give us a number of states. Okay. Okay. So we'll move on to the next analysis, that is the JK flip flop. For JK flip flop. So if you see here, our an plus 1, bn plus 1 did not have much difference here because this q is basically d. Q gives whatever the d gives. So we do not have much thing to solve when we are trying to find an plus 1 and bn plus 1. But for jk flip flop itself has a characteristic uh, thing, right? So function, what is the characteristic function of jk flip flop? Jkn plus 1. So what is it? This is 0 0 0 1 1 0 1 1. So what is the characteristic function for this? A characteristic table for this.
It will be Qn
Mm-hmm.
0 1 then Qn bar.
Correct. So we have this will, when it is 0 and 0, it will have the current state as it is. 0 and 1, it will reset it. And when it is 1
Set
and
when it
0,
will set
yes,
and then
correct.
complement.
Yeah, it will toggle it. Correct. So this is the JK flip flop. Now let's go and I will draw the JK flip flop here. Now we'll draw FSM with JK flip flop. And here I'm having just one output, A. So here, let's say I'm having an AND gate to give it to K, and for AND gate, let's say I am using a complement, and this is from B. Okay, and this is B. Okay, from B here, I'm taking here to J. And here J, this has X bar. And here K, it has, we are using a XOR here. So this is A. So the input, this is A, and I have another input which is X. Here X. This is X. Okay, so JK, JK, AB, everything is given. Okay. So if you see here, for this one, we do not have output. Only we having primary input. And here our combinational block will be this part. So this will be our combinational block. This will be a combinational block 1. And we do not have combinational block 2. And similarly, we do not have output also. Okay. So now we follow the same thing. First, we start with state equations. For that, let's see, I have this part U, V, W, and X. So now what is my U? So U is basically B. And then we have, okay, before that, let's just find N. What is our N? Number of flip-flops is 2. And what is our M? 1, right? It is 1 and K is 0. Output is 0. M is input, K output. So U. Now next is V. So V here is basically AND gate for X bar and B. So V is B X complement. Now W. So our W here is X bar and X. Okay, let's just not use X then. Let's say it is a Z. Okay, let's say this is it. So the Z will be A, A, and XOR of X. So this is A XOR X. Okay. So now if you say this is J A n plus 1, this is K A n plus 1, J B n plus 1, K B n plus 1. So similarly, we are having this U is J A n plus 1. J A n plus n, and what is it? It is B. Then we have this is K A n plus 1, and that is Bn. Okay, this is Bn X bar. And then we have JBn plus 1 X complement, and KBn plus 1, that is AN XOR X. So this is our state equation. Okay. Now once we find our state equation, what do we have to do? We find our state table. For the state table, we will have present state, we have our input, we have next state. We don't have output for this example, so we'll skip it. And then just because this is a JK flip-flop, we should also understand the flip-flop inputs. So we have our flip-flop inputs. So here our present states are AN, BN, input is X, next state is AN plus 1, BN plus 1, and our flip-flop inputs are JA, KA, JB, KB. Okay. So now let's say we are writing, or let me just copy it from here. Okay. So now we got our, we have our present state and we have our inputs. Now we have to find our next states. So before finding our next states, we know here that our JA, KA, JB and KB is what we can find. So our next state depends on that flip flop. For D flip flop, you didn't have any issues because basically the output itself will give directly from the D, like Q is equal to D. So it was not a problem. But here, what you have to do, first you will go ahead and fill the JK outputs here. Okay, so now if you say JA, that is basically BN. Okay, so our JA is basically BN. So B, that is our JA. So you have 0 0 1 1 0 0 1 1. And then our KA, what is our KA? It is BN X bar. BN X bar. So what is it? What is Ka? It is B n x complement, right? So what is it? B and we have x. So what is K?
0,
Yes.
then again 0,
Yes. Again 0,
1,
1,
0,
0,
0,
0,
0,
0,
1, 0.
0. Correct. Now JB. So what is our JB? It is x complement. So we will write complement of x. 1 0, 1 0, 1 0, 1 0. Now KB. KB is A and X the XOR. This row and this row. We find the XOR for this row and this row. So 0 XOR 0, 0. Then
0,
0, 1, 1, 0, 1, 1, 0, 1, 0. Okay. So we found our flip-flop input. Now comes our next state. Now we have to find our next state. How do you find your next state? We have our excitation table, right? So this table here, where if j and k is 0, what will be our qn? Our qn plus 1 will be basically the current state, or it is set to, so basically this is reset, set and toggle based on j and k. Now for this row, we will consider J, K, and A to fill this row. So now 0 and 0, what should happen? It should retain that particular current output. So the
it will
current,
be 0,
yeah, current state is 0. 0 and 0, current state.
0 again,
1 and 1, toggle.
it will be
So it,
1,
correct. And 1, 0, set. No, we set. So it is 1. Then 0, 0, it is again
1,
current state. Then 0 0 again current
1,
state. 1 1 will be,
it will be 0,
we will toggle, and 1 0 is again
1,
1, basically set. Now similarly we come for Bn. So Bn plus 1 we will find from JB, KB and B. So now 1 0 is 1, 0 1 is 0, 1 0 is 1, 1 0 is 1 because in J and K 1 0 will set it, 0 1 it will reset. Same thing, 0 1 0, 1 1 we will toggle the present. So the present state is 0, we will toggle it and it will become 1. 0 0, same state, and then we will have 1 1, toggle the present state. So 0 0 0, retain the same state. This is our An and Bn plus 1. So now this is the entire table, the state table, where it has present state, input, next state, and flip-flop inputs. Okay. And now finally, after we are getting the state table, we will move on to state diagram. Okay, state diagram. So for the state diagram, now how many states do we have? Will we have? We have two flip-flop, right? So how many state will we have?
4,
Correct. We have four states. Why? It is because 2 power this 2. 2 power 2. Four states we will have. So let's see a state 0 0, 0 1, 1 0, 1 1. And now from here at 0 0, it will here just see this entire thing. We do not want the JK. We just want this entire thing. So from 0 0, it will move on to 0 1 and the input is 0. So 0 0, it will move on to 0 1, and the input is, so let's say from 0 0 it will move on to 0 1, input is 0 0 0, it will move on to 0 0, input is 1. 0 1 to 1 1, the input is 0 0 1 to 1 1, the input is 0 0 1 to 1 0, 0 1 to 1 0, and what do I write here, the input? Using here 0 1 to 1 1 0, what is the input?
1.
Correct, it is 1. And now the similarly will continue, so 1 0 will move to 1 1, it is 0, and then we have 1 0 to 1 0, that will give us 1, and then 1 1 to 0 0, and that will give for the input 0, and 1 1 will move to 1 1 for input 1. Okay, so basically this is our entire state diagram for this example. Here also we did the same thing. So what did we have? So we have a JK flip-flop example. So from this we found out the number of flip-flops. We have 1 input and 0 outputs. And then we came to a conclusion. We got the state equations. And what are the functions? So the state equations, these are the functions of the inputs and the current state. And once we found the state equation, based on that, we came up with a state table. So our state table has present state, input, next state, and even the flip-flop inputs. Once we got a state table, from the state table, we came to state diagram. Okay. So the next one will be T flip-flop. So it will be analysis of T flip-flop. Or okay, or I'll just stop here for today. So we have, so this is the analysis for T flip-flop will be pretty much like JK flip-flop, because even for T flip-flop we have to understand that if it is going to toggle or not toggle. So we will like look into an example of analysis of T flip-flop in the next class. Okay, and after the analysis we will move on to designing. So for designing again we will use D flip-flop, JK flip-flop, and T flip-flop, and so on. So now, do you have any doubts in this session or anything else? Okay, then if there are no doubts, then in the next session we will continue with the analysis of T flip-flop and the designing phase of it. Okay.
Thank you, ma'am.
Okay then. Thank you everyone.
Thank you,
Thank
ma'am.
you.